So there's a line in your textbook here on page 246 that I think every calculus student, every first-year calculus student should read and think about, because it's a big deal. It's going to blow your mind open here. The difference between calculus and any other math you've done. So what distinguishes calculus from algebra is calculus's ability to deal with variables that change over time. So that's different from just finding a different ordered pair that's a solution of an equation in two variables. It's acknowledging that in the real world, sometimes we have change occurring, and we want to understand that change as it happens. Calculus gives us lots of tools to deal with that no math that you've done before in junior high or middle school or high school has done. So think about this equation that you probably know. It relates the volume of a sphere to the radius of a sphere. Volume is 4/3 times pi times the radius cubed. You know this formula already. You know that if you've been given the radius of the sphere, you could figure out its volume. You know that you could, if you knew the volume of the sphere, you could figure out its radius. You could take that equation and you could use algebra to rearrange it so that the r is isolated instead of the v. You know how to do lots of stuff with this formula. But you've never, until today, you're going to do it now, you've never solved a problem about a sphere whose volume was actively changing. But let's acknowledge that could happen. Think about a bubble, if you're blowing bubble gum, or this balloon, this bubble that's getting blown. You could have a sphere whose volume is changing, and you might want to be able to talk about how fast that volume is changing. Because you can imagine this guy could be blowing the bubble faster or slower. That could change lots of things, how likely it is to pop or how big the radius is going to get before it pops. So we can answer questions about the rate at which the volume of this bubble is changing using what's called related rates. That's the topic of 4.6. The key to related rates is remembering what we know about implicit differentiation. Remember, Chapter 3 gave us all these tools for finding derivatives. Chapter 4 is going to give us reasons to remember and want to use them. So the thing to remember here is how to perform implicit differentiation. So, reminder. I have an equation. It's not a function. Y here is not a function of x, but I do have this relationship, x squared plus y squared, or y squared plus x squared equals 17. If I graph that, that would be a circle whose center is the origin, whose radius is the square root of 17. So it exists. We know how to graph it. We know what it looks like. We can say a lot of things about a circle. But if we want to find the slope of the circle, dy dx, a derivative, something to tell us about how y changes with respect to x, we need to use implicit differentiation because we do not have y as one single function of x. So recall what we did, because you're going to need to remember it in like one more minute. So here's my original equation, y squared plus x squared equals 17. We said that we could take the derivative of both sides of this equation with respect to x. So the second part of this equation, taking the derivative of x squared and the derivative of 17 with respect to x, no big deal. That's the easy part. What's interesting is remembering how we take the derivative of y squared with respect to a variable that's not y. So the derivative of y squared with respect to x is, I stop for a minute and I pretend I'm taking the derivative of y squared with respect to y. Well, the derivative of y squared with respect to y is 2y, so see that I have that y there. And then I multiply by the derivative of that variable that was there with respect to the variable that I wish it was. So the derivative of y squared is 2y times the derivative of y with respect to x. This 2x comes from taking the derivative of x squared with respect to x. That didn't require any gymnastics because I was taking the derivative of x squared, a function of x, with respect to x, the variable that's there. And then the derivative of any constant with respect to any variable is going to be 0. Notice now that I have this expression dy dx, which is the thing I want. That's how is y changing with respect to x. That's one whole symbol that means the slope of y. I can isolate. I use algebra to isolate it, and I get this expression for the slope. It's interesting because notice now here, before we knew implicit differentiation, this had never happened. But now the slope of the function, it's not a function, the slope of the curve does not relate just to the x value, but relates to both the x and the y. We say dy dx is a function of both x and y. It has both x's and y's in its expression. So we can do the same thing. There was nothing special about x and y. Obviously, we use x and y more than we use any other variables like in the universe. But we really, really, really could use any other variables we want. I could have written this problem. I could have told you that p squared plus t squared equals 17, and I could find an expression for dp dt. I would have taken the derivative of both sides of that equation with respect to t, and the algebra is all the same. I get this expression, which looks like this. It's just that everywhere I had y's, now I'm using p's, and wherever I had x's, now I'm using t's. So there's nothing magical or privileged about x and y. So for some students, that's the trickiest part of 4.6, is we're much more likely to use more interesting variable letters than just x and y. But the calculus that we're going to do, it's all implicit differentiation, which you mastered back in chapter 3. So go back to the soap bubble. The volume is increasing as time goes by, so as time increases. So the rate at which the volume is increasing is the rate of change of the volume with respect to time. If we want to use notation for that, we would call that dv dt, the rate of change of the volume, capital V, with respect to time, little t. So look at this formula for volume, the one you know, volume of a sphere. If you look at that and say, I want to take the derivative, that's fine. We know how to take the derivative of volume with respect to r because r is the variable that's there. When we want to find the rate of change of the volume with respect to time, that means I'm going to need to take the derivative of both sides of this equation with respect to time. And I have that implicit differentiation problem, which is I need to take the derivative of 4/3 pi r cubed with respect to a variable that is not r. So that's when I'm going to pretend for a moment that I want to take the derivative with respect to r, the one variable that's there. The 3, which is the exponent on r, is going to come to the front and multiply the 4/3. So the 3's will cancel, which gives me the 4. The pi is a constant multiplier, so he's still there. The new exponent on r is going to be 1 less than the old exponent. That's how I get an r squared here. And then to acknowledge the fact that I was taking the derivative with respect to the wrong variable, I'm going to multiply by the derivative of that variable with respect to the variable I wish it were. In this case, I wanted to be taking the derivative with respect to time. So that's how I get this expression dr dt. And think about what that means, dr dt. Well, that's the rate of change of r with respect to t. And I know that r in this problem is radius and t is time. So this is an expression for how the radius is changing with respect to time. So is the radius getting longer, or is the radius getting shorter, or is it, increasing and then decreasing in length? And so what you notice is that the rate of change of the volume with respect to time, what we call dv dt, is related to, it's a function of, you compute it by using the value for dr dt. So how the volume changes is related to how the radius is changing. And that's how we get this term related rates. The change in one variable with respect to time has to do with, is related to, is a function of how another variable is changing with respect to time. So now we can finally get around to that first question that's on your paper, right? So we have been given this formula for volume of a sphere, and we've been asked to write an expression for the rate of change of volume with respect to time. And we're going to do exactly what we've already done here. Volume is a function of r, but I can still find out how volume changes with respect to time by taking the derivative of both sides with respect to time. We're going to do exactly what I said, which is pretend for a moment I'm taking the derivative with respect to r. That's how I get 4 pi r squared. Remember, the 3 that comes down from the exponent is going to multiply with the 3 that's in the denominator and cancel. That's how I have no 3's left. And then we're using implicit differentiation. We took the derivative with respect to a variable that is there. Now I need to multiply by the derivative of that variable with respect to time, the variable I wanted to be differentiating with respect to. So the rate of change of the volume with respect to time is equal to 4 pi r squared times the the rate of change of the radius with respect to time. So those are the words that say what the relationship between those values is. If I was going to read this just in class or just because I was reading a math problem to one of my friends, I say dv dt equals 4 pi r squared dr dt. dv dt and dr dt, they're both rates of change. They're both derivatives. They're both derivatives with respect to time. And you notice we have an equation that relates them, so they are rates that are related. We say related rates. So here's what is even more fun. Now that you have an equation that relates how the volume is changing to how the radius is changing, and if you know some things about maybe how fast the radius is changing, you can actually compute an expression for the rate at which the volume is changing with respect to time. So notice here, if we happen to know that the radius is increasing 0.1 centimeters per second, so every second it's getting 0.1 centimeters longer, so the radius is increasing. What do you think is happening to the volume of the sphere? Is that increasing or decreasing? Well, if the radius is increasing, then the volume has to increase, because the volume depends on the radius and only the radius. There are other kinds of relationships where we might have two variables to depend on, and there won't be such a obvious answer to that question. And if we know that that is true at the exact moment when the radius is 10 centimeters, so now imagine this guy blowing this bubble, and at the exact moment when the radius of that bubble is 10 centimeters, we take this picture. Really, the radius keeps going, right? But we're going to freeze it in time for just like half a second so we can stop and think about it. If at that moment the radius is 10 centimeters, I know dr dt, the rate at which the radius is changing with respect to time, is 0.1 centimeters per second. I can now compute how fast the volume is changing at that moment. Spoiler alert, it turns out that like half a second later, or half of a second later, it's changing at a different rate. But at this one moment in time, I can freeze it and I can answer this question. How fast is the volume? How fast is the sphere, the bubble, getting bigger at the exact moment when the radius is 10 centimeters? So I have this formula. I'm going to do some replacing. I know dv dt, the rate of change of the volume with respect to time, is 4 pi times r squared times dr dt. So you can see I've rewritten that same expression. There's the 4, the pi. R is 10 centimeters, so r squared is going to be 100 centimeters squared. And dr dt, we've been told, is 0.1 centimeters per second. So we can do some multiplying there and simplify, and I find out that dv dt is 40 pi cubic centimeters per second. And think about what that means. That means that this only applies to that 1 second, that one moment in time when I was computing. At the exact moment when the radius is 10 centimeters, the volume of the sphere is increasing 40 pi cubic centimeters every second. Notice these units. Where do these units come from? Cubic centimeters per second. This was centimeters times centimeters times centimeters per second. So centimeters times centimeters times centimeters, centimeters cubed per second, so divided by seconds. That's how I get those units. But then think about what that means. Those units have to match what would make sense for a rate of change of volume with respect to time. In a problem where all the lengths are measured in centimeters, volume is going to be given in cubic centimeters. And in a problem where times are all given in seconds, dt, a very small change in time, is also going to be measured in seconds. So notice volume here, cubic centimeters per unit of time, second, just to convince yourself that these are the correct units.